In this video, I want to talk about determinacy and stability for beam, truss, and frame analysis. So first off, to define what this means, basically when all of your unknown forces can be determined by your equations of equilibrium, then you have what we would call statically determinate. So let me just write this criteria out. So if you have your number of unknown forces and the number of equations of equilibrium. And again, if these are equal, then you have a statically determinate structure. So, what if the number of unknown forces was greater than the number of equations of equilibrium? Well, then you have a statically indeterminate structure. And that just means you aren't able to solve for your unknown forces with your equations of equilibrium, and you will have to introduce compatibility equations in order to solve for your forces. So what if it's the other way? What if the number of unknown forces is less than the number of equations of equilibrium? Well, then you have an unstable structure. So for both of these first two cases, when your unknown forces are equal to equations of equilibrium, or if your number of unknown forces is greater than the number of equations of equilibrium, these are both stable. However, if they're not equal, then you have a statically indeterminate structure where you will require compatibility with the equations. And I'll go into what compatibility equations are in a later video. And you will need the number of compatibility equations that you will need depends on the degree of indeterminacy. So the number depends on the degree of indeterminacy. So for a beam, your number of unknown forces are basically your reactions. So like if you have a pin reaction, you have a reaction in the x direction. So if you have a pin reaction, you have a reaction in the y and a reaction in the x. So reaction x, reaction y. So that's 2. That's yeah, that would be 2. So if you have a roller support, as you would recall, this only has a reaction in the y, so this would just be 1 reaction. So the number of equations of equilibrium for a coplanar structure is always going to be 3 plus the number of equations of condition. So I'll label that as C. So C is equations of condition. So equations of conditions are basically points in your beam where you know a certain condition, such as an internal hinge. So if you have an internal hinge in a beam, so we have a pin support there, roller support there, this is a hinge, internal. We know that the moment there is 0. So that gives us an equation of condition. So that would be, C equals 1. So we would get one extra piece of information there. For an internal roller, so that's a hinge. For an internal roller, it would be drawn something like this. So this is a roller. RC equals 2. It can also be drawn this way. Hinge, 2 hinges. So yeah, for internal rollers, our equation of condition is 2. So let's see. So let's do some examples. So for this simply supported beam, we want to determine whether this is statically determinate, statically indeterminate, or unstable. So again, we need to find the number of unknown forces, which for beams, so these are all beams, our number of unknown forces are basically our reactions, as I've written down here. Number of unknown forces is our reaction. So how many reactions do we have? Well, we have 1, 2 for the pin support, and 1 for the roller support. So that gives us 3 reactions. And how many equations of equilibrium do we have? So basically this automatic 3 comes from your sum of forces in the y, sum of forces in the x, and sum of moments. So sum of moments. So sum of moments, sum of forces in the x, sum of forces in the y. That's where these 3 equations come from. So we don't have any internal hinges or rollers, so our C is just 0. So our equations of equilibrium equations are going to be 3. So they are equal. So this means that this is a statically determinate structure, and also stable. Again, as I mentioned before, if it's statically determinate or statically indeterminate, they're both stable. Moving on, let's do another example. So what if we had an internal hinge and a roller? So pretty much similar to the previous example, but now we have an internal hinge here. So that's an internal hinge. So again, our reactions, we have 1, 2, 3. Our equations, we have the 3 coming from sum of forces in the x, sum of forces in the y, and sum of moments, plus 1 equation of condition. So 3 is less than 4, which from our requirements earlier, or conditions, we know that if our number of unknown forces is less than our number of equations of equilibrium, the structure is unstable. So this structure is unstable. Example 3, we have fixed support with an internal roller support, and another roller support. So let's count our number of unknown forces, which is our reaction. So we have one here, and one here. We have one vertical here and one vertical here. So if we count those up, we have 1, 2, 3, 4, 5 reactions. And if we count our equations, we have our 3 plus, this is an internal roller, so that counts as C equals 2. So our C there is 2. So 5 equals 5. So this is a statically determinate structure, and of course it's stable. Let's look at another one. I got plenty of examples here. So this is example 4. Here's something new. So we have a fixed support with a roller, so it allows the beam to move up and down, but it cannot have any moment, or it will have a moment at that support, and it resists it in the horizontal direction. So again, we'll count our reactions, which we have 1, which the fixed support can resist the horizontal force, and then it also has a moment, but it does not have any vertical reactions. This roller has a vertical reaction, this pin has a vertical and a horizontal. So we have 1, 2, 3, 4, 5 reactions. And our equations, we have 3 plus 0. We don't have any internal hinges or internal rollers, so 5 is greater than 3. So this is statically indeterminate, and the difference, the difference between the reactions and the equations is the degree of indeterminacy. So this is statically indeterminate to the second degree. So this means that we will require 2 compatibility equations in order to solve for all of our unknown forces. So again, as I mentioned earlier, I said that when you have a statically indeterminate structure where the number of unknown forces is less, the number of unknown forces is greater than the number of equations of equilibrium, you will require compatibility equations in order to find all of the unknown forces. And again, that number of compatibility equations that you will require to solve all the unknowns depends on the degree of indeterminacy. And in this example, we have statically indeterminate to the second degree, so you will require 2 compatibility equations. So I have one more example here. It's kind of out of the ordinary. So another hinge. and a pin support. So these are hinges. Oop, can't spell. Hinge. Alright, so how many unknown forces do we have, or reactions? Well, we have 3 for this fixed support. Oops. 1, 2, 3. We have 1 here, and we have 2 here. So if we count those up, we got 1, 2, 3, 4, 5, 6 reactions. And we have how many equations? Let's see. 3 plus these hinges count as 1 each, so 2. So 6 is greater than 5. So by our previous conditions, we would say that this is statically indeterminate to the first degree. However, this structure has an internal instability, and the reason for that is because of, let me get a different color, is because of this guy, and this guy. When we look at that, just by visual inspection, we know that it's gonna probably sag here because of these 2 hinges. And one definitive way to know if there's an internal instability is if you have 3 moments that are equal to 0 in a row in a structure, then you will have an internal instability. So again, this is all lying on the same axis, and we have 3 points here, 3 nodes here, that where all of the moments are 0. So because of that, we have an internal instability. And even though the number of unknown forces was greater than the number of equations of equilibrium, we cannot say that this is statically indeterminate to the first degree because of this internal instability. So yes, this is an unstable structure. Okay, so that's all I have for beams. In the next video, I'll talk about analysis for trusses as well as frames. So stick around.